So it's in class assignment.
So it's on the computer, we don't have to handwrite it?
That is correct. You need to type on it though. So I'm gonna, it should have come into your hats off, please. It should have come into your classwork feed, and we'll go through some notes, and then we'll go the last 15 minutes or so, talk about the lab questions. Hopefully that will all go well. Stinking power outages. PG&E needs to get their poopy together. It's really annoying. Well, their explanation is for March it was, you know, bad stuff, and in April it was bad stuff, and yesterday or Saturdays was trying to make repairs and their backup went out. It's like, dude, annoying. Oh well, it's just frustrating when you have a well and that means you can't have water.
Someone else to come to California.
Hey, all right. Oh well, it's okay. We're fine. We're fine. Yep, that's the one. So this is what you're going to write on. I'm going to get you a little intro right now at the top that you can type in. And then we'll talk about these other things. We're going to watch part of one of these videos, but if you need more explanation, there's a second one as well that might help. So that's fifth period's lab. This is your lab. This is that. This is that. All right. I'm going to do this. So there's 3 words on your paper, and I'm just going to write it down. Solution, solute, solvent, and solution. So a couple things to point out to you also. This one has less letters. Solute has the fewest letters. Solvent has more letters. Solution has the most letters. So why did I make a big deal about that? Well, what is a solution? We learned this way back when we were learning about mixtures and stuff. It's what? What's a solution? What's a fancy name for a solution? A mixture. Special kind of mixture. Homogeneous mixture. So it looks uniform throughout. However, there's stuff in it. It's not pure. Okay, but it might look kind of pure because the color is the same or whatever. The total solution is composed of 2, sometimes more than 2, but we're just working with the simplest, 2 parts. One part is called the solute, and this is the lesser amount part. I'll hopefully explain that here. And then solvent is the greater amount. Now, why do we make a big deal of this? Why don't we just say, God bless you, that the solute is a solid and the solvent is a liquid, and they make a solution, an aqueous solution, for example. Exactly. It's not always like that. Is it sometimes? Of course. So we could have solid sugar and liquid water and make an aqueous solution of sugar water, like I do for make my stuff for my hummingbirds every day. Every day I have to make more. It's crazy. I have so many. That's a good thing. So it's sometimes like that, but not always. Okay. Not all solutions are in a liquid format. Okay. There can be 2 gases together. For example, the air you're breathing right now is a solution. Primarily oxygen and, oops, that was a really bad 7, nitrogen gas. Okay, so we can have a solution of gases like you're breathing. We can also have a solution of liquids. For example, hydrogen peroxide and H2O can go together to make hydrogen peroxide solution that you buy. So the hydrogen peroxide that we used in our lab, and that you, if you have some at home, is probably the same concentration, is 3%. 3% of it is H2O2. The other 97% of it is water. lesser, greater, lesser, greater. Okay. And then finally, we can also even have a solution of solids, aka an alloy. For example, copper and silver together make sterling silver solution. Okay, about 5%. I don't know if it's, yeah, let's just say 5% copper and 95% silver. So copper would be the solute and silver would be the solvent. Okay, most of us think of solvents as being a liquid. It doesn't have to be. And of course, we can have gases in liquids too. And could we have gases in solids? Nah, we won't go there. We won't go that far. But it's not just a solid and a liquid. That's what I want to emphasize to you. Okay, everybody good with that? Solute, lesser amount, solvent, greater amount, solution, both of them together. Okay. All right, we're going to pick up on the PowerPoint here. Why is this a big deal? Well, all the reactions that happen in your body happen in solution, for one. Solutions are a big deal. Not everything is soluble. That is also a big deal and a good thing. Otherwise, we'd all be floating around together and something, I guess. That'd be kind of weird. And also, pure water, clean water, drinking water is a big deal. Not everybody on the planet has clean drinking water, whether there's toxic chemicals in there or heavy metals or pesticides, herbicides, all that kind of stuff. It's a big issue is having clean water. We are really blessed in this country that we have mostly clean water, most places, but not every place, even in the United States, has good drinking water. All right, concentration, super simple. You should know this. One thing with concentration, you will see in college chem is concentration is often put in square brackets. So there'll be a number in there, okay? And so a shorthand way to write the word concentration, instead of writing out that whole big old multiple syllable word, is just write square brackets. So you get your, it's like everybody knows that this means and, or this means and, or this means and. You don't have to write, or BC means because. WT, no, I can't go there. Never mind. Okay. There's lots of shorthand you can use, right? So one shorthand is concentration, square brackets. Obviously, you should probably be able to figure out, you can have a dilute solution. Doesn't have very much stuff in it. Or you can have a concentrated solution. For example, when you buy orange juice, if you buy it in the little cans, okay, the little can of OJ is concentrated. So they juice the oranges and then evaporate off the water. And so then you add 3 more cans of water to dilute it. Close to drinking concentration. Yep.
And what exactly is it that defines what is solute?
Solute is whatever's the lesser amount. Yep. Whether it's by volume, whether it's by mass.
So that's it.
Yep. Technically. So again, most people's brains, a solution is in a liquid. It's a solid in the water. Water is the universal solvent. So it dissolves almost everything. Thankfully, it doesn't dissolve us, but that would, unless you're the Wicked Witch of the West, but anyway, okay. So dilute means you put in like a 4th can of water or something like that. My mom used to make Kool-Aid for us when we were kids. Have you ever seen the little Kool-Aid packets that are unsweetened? It says add 2 cups of water to the container. She only ever added 1, but she gave us all the red dye anyway, but not the sugar. So, anyhow, just something else to think about. Okay. So dilute doesn't have very much in it. Concentrated has a lot in it. Pretty straightforward, I think. Okay, the most important way of doing concentration in chemistry is molarity. And we've talked about it already. It's abbreviated with this italicized, oh, not quite that crazy. That looks like mu. I'm getting crazy in my old age. Crazier. So molarity is equal to the number of moles of solute divided by the number of liters of, they never say this explicitly, but I want to emphasize it, final solution volume. A lot of times what you'll just see is moles per liter, and that's not quite enough information. So I'm going to make up, this afternoon, I'm going to make up some 1 molar sodium hydroxide solution because I need it for our little bottles. I buy this big old container of this white stuff. So sometimes it comes in flakes. Sodium hydroxide comes in flakes, or it comes in little pellets. I'm going to measure out 1 mole's worth of sodium hydroxide and mix it in a volumetric flask to get exactly the right concentration. So if I wanted to have 1 mole of sodium hydroxide, I need to get the right mass. So find your periodic tables. What's the mass going to be? Molar mass of sodium hydroxide. Take a minute and see if you can figure it out. So sodium is what molar mass? Bethany. 22.98977. What do you think? Yeah. And then oxygen, everybody knows, is 16. And hydrogen, everybody knows, is 1. Okay, so if I want 1 mole of sodium hydroxide, that's I said sodium hydroxide and I started writing it again, sorry. I need 40 grams. Okay, I am not going to put exactly a liter, 1 liter of water with that. I'm going to put the 40 grams of sodium hydroxide in my volumetric flask, add some water to dissolve it, and then eventually fill it up to this line. So I have a liter of solution. So it's not 1 liter of solvent, it's the total volume. So, you know, like when you're making, well, I'll go back to my hummingbird feeder, food. I put a pot on the stove, I boil the water, and then I put in the sugar. What happens when I put in the sugar? The volume goes up, right? Sugar is matter. It has mass and volume. It takes up space. And so it'll cause the volume of the liquid to increase. So it's not, I don't put exactly a liter in here either because the sodium hydroxide is going to increase the volume in here. Okay, so we just make it to a total solution of 1 liter, not a liter of solvent. I know it's ticky-tacky and, you know, that seems like really kind of silly, but it's a big deal when you're making up concentration. Okay, it will come out a different volume if I put in a liter. So that's molarity, the most common form of concentration. So we were dealing with 1 molar hydrochloric acid and 6 molar hydrochloric acid. This has 6 times as much hydrochloric acid in that same volume. Okay, so it's more concentrated. Now, you could also make half molar solutions. So if I want a half molar solution of sodium hydroxide, what would I do? Divide it in half. It's really not, it's super simple. 20 grams per 1 liter. Okay, and that would, a final solution, that would be what you do. So again, you put it in, you add some water, get it to dissolve, and then you fill it to that etched line that's exactly a liter. So I have 1 mole. right? Cute little mole. And 1 liter. If I put my mole in my 1 liter, what do I have? One. What's the concentration? 1 mole per liter, 1 molar concentration, right? What happens if I put in half a mole? I have a half molar solution. What do I have left? Molasses. No. I've been waiting all year for that joke. Thank you. I hope you laughed at home too. Chemistry jokes. Yeah. So if you made a mole for mole day, some people used to make moles for mole day. Obviously, you can see. And the pattern has the directions on how to make it, so they come apart for this joke. Okay. What are you going to do with me? I don't know. All right, we're going to watch this little quick. Does that show up on your screens when I do this? Or no? Okay, good.
The concentration of a solution is a measure of the number of particles of a solute, a dissolvable solid, which are in the solvent, the liquid in which the solute is dissolved. What might you say about the number of particles in a concentrated solution compared with a dilute solution? Pause, think, and continue when ready. The number of particles in a concentrated solution is greater than the number of particles found in a dilute solution. Think about when you sweeten a drink by adding sugar. The more sugar you add, the sweeter the drink tastes. We can calculate this using 2 formulae and accompanying formula triangles. The first way of calculating...
So they're going to use this triangle thing. It works really well. It's also used for finding density. I don't think it's that hard, but molarity is moles per liter. So you have to divide moles and liters. If I wanted to get moles, I'd multiply molarity times liters. Why would I want to get moles? Because moles tell us the number of particles. And that's what interacts when we do chemical reactions. Okay, we need the right number of pieces of everything to do the reaction. And so in solution, there's particles floating around. They have to have the right number of them to make the reaction complete. If I wanted to find liters, I'd have to flip it around and multiply both sides by this and divide both sides by this. I divide moles by molarity. Okay, so if your triangle makes sense, great. If it doesn't, don't worry about it.
Concentration is to use moles, an amount of a chemical substance, and divide it by its volume. Here's the formula triangle for this. Most of the time, volumes are measured in cubic centimeters. So 1,000 cubic centimeters is equal to 1 decimeter cubed, or 1 liter. So, how many decimeter cubed is 500 cubic centimeters?
It's not a trick
Pause,
question.
Think, and continue when ready.
So there's a couple of things that get used in chemistry that we don't always use in this classroom, and our textbook doesn't have it. So 1 gram of water is 1 milliliter of water equals 1 cubic centimeter of water. Okay, so again, the cool thing about the metric system, one of the many, is that linear measurements can go to volume measurements. You could do how many cubic inches in a gallon, but it would be really a pain in the backside to figure out. Okay, so this is a nice clean one. If you have 100 centimeters, you have a meter, and if you have 1/10 of that, that's a decimeter. So what's a decimeter? It's 10 centimeters. If you have 10 centimeters times 10 centimeters times 10 centimeters, you have what? 10 times 10 times 10? 1,000 centimeters times centimeters times centimeters, and it is a liter. It's 1,000 cubic centimeters, which is 1,000 milliliters, which is 1 liter. So 1 decimeter cubed is the same as 10 times 10 times 10 centimeters is the same as a liter. Okay, they're the same thing, so they're interchangeable.
Is there advantages using
Get the answer.
What's that?
Is there advantages using decimeters?
I don't think so, but it's used a lot. So
You need to divide 500 cubic centimeters by 1000. So 500 cubic centimeters is the same as 0.5 decimeter cubed. Did you get it right?
yes.
You can find any of these quantities by covering up the one you're looking for with your finger. For example, if you cover moles, you can find this by multiplying the concentration by the volume. This is because any two terms on the bottom of a formula triangle are always multiplied together. If you want to find the concentration, you cover this and divide the number of moles by the volume. Let's try this now. If you have 2 moles of salt and dissolve it in 2 liters of water, use the formula triangle to
You don't need the formula triangle. What's 2 divided by 2? 1. It's kind of silly.
solution. Don't forget the units.
1 mole per decimeter cubed.
2 moles divided by 2 liters is equal to 1 mole per decimeter cubed. Did you get it right? And did you include your units?
Yes.
The second way of calculating the concentration is very similar, except sometimes we use a mass of a substance divided by volume rather than a mole of a substance. The formula is mass divided by volume and has the unit grams per decimeter cubed rather than moles per decimeter.
It's really that simple. So I could also, oops, I already erased it. Sodium hydroxide, 40 grams per decimeter cubed is 1 molar sodium hydroxide. Okay. So we're going to stop there because I don't think the triangle maybe is all that helpful. And we got Professor Dave. There's a link to his on the sheet if you're interested in looking. So again, other ways to do it, grams per liter, AKA grams per decimeter cubed. And then 2 others that are pretty common, parts per million, ppm, or parts per billion, and then percent by volume or percent by mass. So hydrogen peroxide is percent by volume. Acetic acid, aka vinegar, is 5%. 5% acetic acid, 95% water by volume. Same with isopropyl alcohol is 70%, most rubbing alcohol that you buy. So it's 70% alcohol. So that's the solvent. And 30% of it's water. All right. So, but we're going to talk about grams per liter really quick. It's just as simple as what he just said. You're taking the mass and dividing it by the volume of a solution. So instead of the number of moles by solution volume, it's the mass in grams by solution volume. I have to change moles into grams so I can weigh it out, so I can do my work anyway. There are also some applications where knowing the solubility in grams per 100 grams is often used. Okay, so we won't have time to get into that, but just so you know, that's another thing. Okay, simple as it sounds. Mass is in grams divided by liters for the volume. Parts per million. What's up? We good?
Calculating by the volume of mass.
Mass solute by volume of solution. And then ppm and ppb are what are used often for talking about toxic things. So contaminations in your water. So if you have a well like we do, you're supposed to get the well water checked every year, or at least every other year. We don't, but you're supposed to. There, I told you the truth. Okay. Why? Because bacteria can get in there, because toxins get in there. This area, the rock around here, arsenic leaches into the groundwater pretty well, which is bad for you in case you didn't know. So having your water tested is a good idea. Great job opportunities working for TUD, working for Hetch Hetchy, which is City of San Francisco's water supply. You can get really good paying jobs if you do water chemistry. Okay. And they are looking for contaminants in the water as well. And that's also an outcropping or outcome from Earth Day, right? There was a river on fire in 1969, on fire, okay? A body of water burning. It was ridiculous because it was so contaminated. Why? Because industry, they were dumping crap in there and garbage and every other thing. So that's why we have the EPA. That's why we have the Clean Water Act. That's why we have these standards to try and minimize the toxins in your water. It's a good thing. Pesticides, herbicides, lead, heavy metals, solvents that are used by the military, solvents that are used in industry. There's all sorts of crud that gets into our water. And once it's in water that's underground, like in our aquifers and stuff, whoo, it doesn't ever get out. So it's really, really a big deal. Okay. So ppm, parts per million, right? Per, dollars per gallon. That's a ratio. It's a fraction. And parts per billion, the really nasty stuff, the really bad stuff, they limit parts per billion. Okay. To do this, you just take the mass of the solute. So they'll take a sample and dehydrate it and figure out how much of the nasty stuff is in there and divide it by the mass of the solution. And again, water is simple, right? 1 gram is 1 milliliter, 1,000 grams in 1,000 milliliters. So you find the volume of the water and then you know the mass pretty quickly or pretty close. There's a little more to it. It has to be a certain temperature. But once you've got that fraction, that ratio, then just tag times 10 to the 6 on the end of it. And that's your parts per million. And if you want to do billion, it changes to 10 to the 9th. Some things in parts per billion are really, really bad for you. Okay. It seems like it's so minuscule, but it still can be bad. If we had more time, which we don't, we'd talk about the crisis in Flint. This made news. It's still making news. Flint, Michigan's water management team decided to stop buying water from a lake because it was expensive. And this is during the economic downturn in the mid 2000s, Michigan. And they started taking the water out of the river that ran by town, and they didn't treat it properly. And here's the problem. The pipes to old houses, and even in this area too, we have some issues. A lot of places have lead pipes. So maybe the main water line under the road is iron, which is what most of that color is. But the connector from that pipe to your house is lead. And you should know, lead's bad for you. It causes mental issues. It causes health issues all throughout your body, especially if you're a little kid still growing. This stuff never gets out of your body. Once it's in, it stays. Heavy metals have no way to get out. So this is what's coming out of their faucets. This is some samples from different people's houses. It's awful. Okay. It causes mental problems. It causes health problems throughout your body, disrupting hormones, all sorts of things. It's really bad. And these people would not admit it. They're still not, some places still don't have drinkable water. They still have to have bottled water. Normally those pipes aren't a problem because there's a layer of minerals on the inside coating it. So the water doesn't actually ever touch the lead after a certain couple of months. It just is hitting the minerals as it goes by to your house. But because they switched the water supply, it was more acidic. It dissolved those minerals, and then it was leaching, dissolving the lead off the pipe and bringing it right into their house. They couldn't. They would have to go. There were showering stations and stuff because you're not even supposed to bathe in that, especially if you're a kid, because you can breathe it in. You can also, you get stuff in your eyes and your mouth when you shower. It was terrible.
And like your hair and like your skin is super like.
Yeah, it was really bad. So. Cause for concern, according to the EPA, is 5 parts per billion with a B. One of the samples at least had 13,000 parts per billion. 5 versus 13,000. Okay. This one from one of the colleges that studies was 158. Flint water had 27. That's still almost 6 times higher than you should have. Okay. And yeah, it's really bad. So it's still a problem. It's an ongoing problem. They still haven't resolved it. And there's other places. It's not just Flint, Michigan that has lead pipes to the houses. So our infrastructure, downtown Sonora, we have those iron pipes. They keep breaking, they keep rupturing. Those were put in like 70 years ago. It needs to get fixed. Percent solutions, percent is just like normal percent. It's a ratio, aka fraction. Volume of solute to volume of solution. 3 milliliters of hydrogen peroxide, 97 milliliters of H2O. Hopefully that gets you. And again, you can also do it with mass. Grams to grams can also be used. So it can be milliliters to milliliters, grams to grams. It just depends on, and each application uses different ones. So I'm sorry, there's other kinds of concentration. Instead of molarity, there's also molality. There's also normality. It's very confusing, but it's not bad if you're always working in that same type of concentration, but there's just more than one. However, again, the most important one for you guys, molarity, number of moles of solute per number of liters of solution. Okay, got to know that. All right, questions? Okay, as soon as you finish typing whatever notes you want to put on there, hit send and pull up your lab really quick. Pull them out of your bags, those of you that are here.
I'm not sure I could do.
You may. Thank you for asking. Okay. There we go. So this is our lab. I think we got, so keep in mind for the questions, there's a lot of the information in the background information, especially like testing the gases. We got through that. We got through that. Got through that. We did combustion. We did combination. Okay, so reaction number 8 was zinc with hydrochloric acid, and everybody had fun with that when we got our little explosion from the hydrogen gas. Question is, what else formed with it? Well, there's zinc and chlorine left over. If you look on your periodic table that has the charges, you'll see that zinc is the +2. Chlorine's always a -1. Chloride ions are -1. Those aren't really observations. I'm just telling you. So if we're going to make zinc chloride, we have zinc and we have chlorine. And how many chlorines do we need? 2. Good. And so since we need 2 hydrogens and we need 2 chlorines, very conveniently, we'll have a 2 for the coefficient here. And zinc chloride will be in solution. And that's again because zinc's higher on the activity series. It can bump hydrogen off of the chlorine. Right, so hopefully you had fun with that. An element and a compound, different element, different compound, what kind of reaction? It's actually not. It's one element, so it's single replacement. Yep. And your splint should have caused a nice whoop in the test tube.
It was actually right.
I think so.
Yes.
Okay, so make sure you've got observations, make sure you got your results, make sure you circled or highlighted if you're at home. And then this last one, we're taking a base, hydroxide, and an acid. And what's happening? It's called innies and outies, right? The sodium goes with chlorine and makes sodium chloride. What's that? Yeah, it's actually table salt. Okay. And the hydrogen from the acid goes with the hydroxide from the base to make HOH. What's that? Water. So you got salt water. So this is a special kind of double displacement. What kind of double displacement is it? Has a special name, acid and a base making salt and water. Oop, I'll let you look it up. Thank you. Okay, so what was supposed to happen is when you put the sodium hydroxide with the phenolphthalein, it should have gotten that magenta pink color. And then you should have added the acid and it should start to clear up. Acid makes phenolphthalein clear, base makes it pink, magenta. The number of drops should have been equal or close to equal, but I haven't been getting that in other classes. Did anybody get them close to equal? Like 10 and 11 or 10 and 12 or something? 12 and 13. Okay. 3 and 4. But you put 10 in. So 10 drops of sodium hydroxide should have gone with 10 drops of 1 molar hydrogen peroxide or hydrogen chloride, because 1 hydroxide, 1 hydrogen should make 1 water. Anywho, so number 1, what's the definition of molarity? That should be easy after today, I hope. Number 2, make sure you list all of the gases, all 3 of them. You can do your questions on here if you want, or do them in pen on your documents on a lined piece of paper that I can read easily, okay? So you're going to turn in your labs tomorrow. List all 6, okay? Every one of them. They're on your graphic organizer, okay? Don't skip them. Just do them in order. What's a catalyst? What does it do? What's endothermic, exothermic? What are indicators? What do they do? What did phenolphthalein do? Questions? Again, if you're not doing it on the Google Doc, do it in ink neatly, please. Any questions from home? Everybody's good? All right, you're free to go. Have a nice rest of your Monday.
What are we doing for finals?
I will talk more about that tomorrow.